First of all, let me welcome all of you to Chennai, though for those who come from other parts of India, also other parts of the world. It's a great pleasure to have you all here for this nice meeting, actually. And Manjari is always enthusiastic, as you will see actually in the next few days. She's always forthcoming for every physics activity that is going on in IMSC. And this is one of the many things that she has been doing for science, actually. So I'm really happy that, this meeting is taking place here because we have a very nice group doing astrophysics and cosmology. And we love other things also in this meeting, some outreach activities on Saturday, I suppose. So it's part of that program, actually. So I won't take too much time. Enjoy, the ambience here and food, of course. And, of course, physics part, I don't have to tell you. Thank you. Have a nice time. Yeah.
Thank you. So I'll hand over to today's chair, Professor Gopakumar. And so our first speaker, Susmita, is already here. So.
Thank you, Manjari. So, welcome to the first day's activities. The first talk will be from Susmita Adhikari from IISER Pune. She's going to talk about compact binary mergers and their, connections to galaxies. So this will be for 50 minutes, I presume she can, and then 10 minutes for discussion. So I hand over it to you. Please take it away, Susmita. Thank you.
Yeah, thank you very much for inviting me to talk at this conference. It's a really nice opportunity to connect with this group. So I'll be talking about today, basically the work that I've been doing on basically linking structure formation and binary evolution. So most of my time I actually spend studying dark matter and halos and how they evolve through time. So this is sort of a new area that I've delved into where I want to understand the connection between the binary systems and the host galaxies that they live in general with how structure evolves through the universe. So, of course, gravitational waves have, detectors have opened up really a new window into the universe. We've been mapping the sky in different wavelengths over the last many decades. And now we are really, over the past few years, we've really just started to map out the sky in sort of a completely new way, which is using these gravitational wave detectors. And we are sort of making a map of these sources through the sky. Currently, so this is just a figure showing how the different gravitational wave detectors, from ground-based detectors to space-based detectors, sort of span the full range of frequencies of gravitational waves, starting with detectors like LIGO and Virgo that would mainly be detecting stellar mass binaries that have high wave frequencies, to space-based detectors that will be detecting binary supermassive mergers, also pulsar timing arrays, and finally, the CMB gives us the measurement of inflationary gravitational waves from the which have the lowest wavelengths. So, with the advent of LIGO Virgo, at least, we've basically been building up our senses of these binary systems, particularly black holes, or black hole neutron stars, or neutron star mergers. And over the different runs of the LIGO Virgo detector, we've basically collected this whole census of objects that are really exciting and are helping us learn about some of the most exquisite, exotic physics in the universe, in some sense. So this is a picture that most of you are familiar with, which is essentially the masses of these compact objects, or as they're as they're called, masses in the stellar graveyard, as when stars die, essentially. And you can see that these are all the different black hole mergers in blue that have been observed. And you have several candidates. We have one candidate for a neutron star merger, and several candidates for possibly neutron star and black hole merger, and so on. So our universe, of course, has all kinds of diverse, interesting inhabitants, right? So even these few years of getting these observations have revealed to us all kinds of surprising, exciting things. Of course, GW 170817 was the first neutron star merger that we detected that had an electromagnetic counterpart. We've detected, lightest known pairs of neutron stars to pairs that have components in the mass gap that have merged to form black holes in the intermediate mass black holes. So essentially, we are really learning a wealth of information, a lot of which has also, in some sense, surprised us in many ways. So, of course, we've learned many basic things, just first order things, and I'll just leave it out there, not go into each of these ones in details, because many of you, because that's not basically the crux of my talk, but it's just important to keep in mind that what we have already learned, what the physical things that we've already learned with the full vast diversity of events that we have already seen. So these binary systems that we are detecting, essentially we think, at least particularly for the neutron star mergers, we expect them to the first order, at least we expect them to follow, if we think that these neutron star systems are, or these black hole systems are forming out of stars, we expect them to essentially follow the evolution of stars in the universe, right? So the evolution of the stellar population and how star formation has grown throughout the history of the universe, starting from, say, the deionization era to today, where we are here, right? And essentially, as we measure these, as we see these mergers, we are, in a sense, this also gives us a handle on trying to sort of understand how these, as we probe deeper and deeper with second generation telescopes like Einstein telescopes, which will actually give us, which will possibly give us mergers that are happening even at high redshifts, out to redshifts 10 even. In a sense, we are also probing the star formation history of the universe going back to the earliest times, right? So these systems that are co-evolving, essentially the binary systems are embedded in the cosmic web, in the galaxies where the star formation is happening. And in a sense, they are telling us they're also an independent measure of the formation of galaxies in the universe, and they can essentially, tell us a lot, in an independent way about how cosmic structure grew in the universe. So, of course, from the point of view of cosmology, there's been a lot of excitement, particularly because because some of these, because if you have an electromagnetic counterpart to some of these events, it gives you, it acts as a standard siren and lets you measure, say, the Hubble constant and cosmic expansion. Of course, we can measure the clustering of these objects. We can try to understand how, what kind of biases these objects have, and whether they are biased traces of dark matter, what are the biases of their host galaxies, and so on. And we can do all kinds of things that will help us basically constrain cosmology in an independent way from the way that we, not completely independent in some sense, but in a way that is independent from what we are usually doing. And their cross connections will be very interesting to see going ahead in the future. Other than that, we can also by looking at the census of these binaries, of these mergers, and in context to their host galaxies, and in context to their distribution, their clustering in the sky, their properties, we can also try to understand the intrinsic properties of the systems themselves, right? The intrinsic properties of the mergers, how do they form? How and when do they merge? Are the populations consistent with our understanding of how massive stars have evolved, how massive stars have evolved, and how they are connected to galaxy formation in the universe. So it's giving us an independent way to check both the intrinsic properties of these mergers and also whether our galaxy, whether the evolution of these stars is consistent with whatever we understood about star formation and galaxy formation in the universe with all the other probes that we have so far. So particularly exciting are the fraction of events that will have electromagnetic counterparts. And also there will be a small, there will also be a fraction of events which will have a small localization, and therefore we will have, we will be able to identify host galaxies for these events as well. So particularly if we have host galaxies, it is very exciting to use these host galaxies to sort of understand more about the physical systems and the properties of the physical systems that we're observing using these observations. All right, so particularly for right, so primarily for compact object binaries, there are two primary scenarios, two primary formation scenarios. One is the isolated scenario where stars form as binary systems in star forming clouds, and then they basically merge. And the other thing is a dynamic formation channel where these systems form in dense clusters like globular clusters or stellar clusters or nuclear star clusters near the central black hole, where they form basically through orbital captures in near the centers of these star clusters by dynamical interaction. So for neutron stars particularly, we think that the isolated scenario is more probable. But essentially, these scenarios can lead to very different host galaxy properties, and we can use them to sort of distinguish, and we can use our knowledge of where these things lie to distinguish between these different channels. So the gravitational wave event GW170817, as I mentioned earlier, was the first binary neutron star merger that was detected by LIGO Virgo. And it had a total mass of 2.74 solar mass, and it was about 40 megaparsec away from us. Because of the exclusive localization, we could, and also because it was a neutron star merger, we observed it essentially in all across the electromagnetic spectrum. It was followed by a short GRB about 1.7, about 2 seconds after the actual gravitational wave signal. And for the first time, we could actually glimpse into the host galaxy of this neutron star merger. So the host, this particular event happened in this galaxy called NGC 4993. So this is just a picture of the galaxy, and the square over here is where the event was localized, where the GRB was seen from. So what are the properties of this particular galaxy? Yeah, so NGC 4993 is a galaxy which has a stellar mass of about 10 to the 11 solar masses. So our own galaxy, for context, our own galaxy, the Milky Way, has a stellar mass of about 10 to the 10 solar masses. So this is a pretty massive galaxy. It has a very low star formation rate. And also we learned that this particular galaxy might be associated with a larger group of galaxies. So it might be bound to a larger group of galaxies. And in general, this was sort of an elliptical shell galaxy. We also know some other things, like the event actually happened in one of these shell-like structures. So all of these things tell us something, basically give us information about the host galaxy of the system, when the binary merged, right? So this is the state of the system essentially when the actual merger took place. So a lot of my work has been trying to understand how to connect the entire timeline of a binary's merger from its formation to the eventual merger to the evolution of the galaxy within which it lies. So in particular, what I mean is that the merger of binary systems is often characterized, is often modeled with a delay time distribution, in the sense that the stars form and they essentially merge after some time. They don't merge instantly as soon as they form, but they merge after some time, which is known as the delay time between the formation and the merger, which is often characterized by a simple delay time distribution as a power law with some minimum delay time, right? So it has a power law alpha and some minimum offset from the initial formation time. So this particular delay time is this power law nature is motivated based on the distribution of the initial orbital separations. But essentially, given that there is if the delay between the formation and the merger of these binary systems are of cosmological order of gigayears or a few hundred million years or even longer, then the galaxy in which these binary systems form can be the galaxy in which these binary systems merge can be significantly different from the galaxy in which the binaries form, right? So essentially, the galaxy itself has evolved significantly between the time that the binary was formed to the time that the binary merges today. So primarily, if we think that neutron star mergers are following the star formation rate of the universe, are essentially following the star formation rate of the universe and offset by this delay time, then there are primarily two ways in which we can get a handle on trying to understand what these delay time distributions look like. Firstly is, of course, the redshift distribution of these binaries themselves, right? So that would essentially, so how the redshift distribution gives us a handle is because if we take the cosmic star formation history in the universe, which is shown here on the bottom left panel, so this is the star formation, co-moving star formation rate as a function of redshift in the universe, then essentially the binary mergers, the binary merger rate is just this star formation distribution shifted by some delay time, distribution. And the other way is if we cannot get the full redshift distribution of these mergers, and what we can otherwise look at is actually the properties of the host galaxies themselves. For example, the stellar mass and the star formation rate properties and their distribution, the population of galaxies in which these binaries merge, will have important hints given what we understand about how galaxies form and how stars evolve within these galaxies, building up essentially the cosmic star formation history. The properties of the host galaxies today will essentially tell us, can also give us an independent way of understanding what these underlying distributions look like. So this is an example of the cosmic star formation history, which is shown here in black. And if you basically vary the minimum delay time and the slope of the initial distribution of delay times, you can see that these different colored curves, which are basically the star formation history shifted by these delay time distributions, you can see that that the redshift distribution essentially can also give us a handle on what the parameters of the actual delay time distribution is. But while we build the consensus, while we build the census of the redshift of these neutron star mergers over a wide range of redshifts, which is actually quite difficult, particularly for neutron star mergers, because you'll be seeing them closer to you. They have the advantage that many of them might have electromagnetic counterparts, and therefore we can also start studying the underlying delay time distributions based on the properties of the host galaxies themselves. So as I was saying, this is just a simple illustration of the fact that the binaries systems evolve with the cosmic structure and co-evolve with the galaxies. So they form inside some gas cloud inside a galaxy. That galaxy, of course, lives in a larger environment, maybe a cluster or a group or an isolated object. That, of course, lives in the larger cosmic larger web of galaxies in the universe, which we think, of course, is embedded in the underlying web of dark matter. So a typical galaxy, so just to make the connection between these binary evolution to the galaxy evolution. So a typical galaxy has, we understand today, has a path through its lifetime. So if we just charted out the star formation rate of the galaxy on the, on the y-axis with time, we see that a galaxy starts off being blue, spiral, and star forming. It eventually, with time, its star formation rate grows until it basically some feedback processes like AGN quenching or environmental processes will eventually quench its star formation rate, and then eventually the star formation rate falls off as a function of time. Right. And the galaxy properties that we see at any particular redshift, at any particular time in a snapshot in the universe's history, the galaxy properties like its age, its color, its current star formation rate, its stellar mass, its environment, all tell us about essentially their evolution through time. And that evolution also strongly depends on the environment or the immediate cosmic environment within which it is lying. For example, a galaxy that lives in a dense cluster is often, even though this looks yellow, it's often red and dead with little or no star formation, whereas galaxies that tend to live in the field are more likely to be blue and star forming. And many of these environmental processes tend to change how star formation evolves within these galaxies. So we have, so if you think of the star formation history of a galaxy, or even if you just take the full star formation history of the universe, which is happening inside of galaxies. So here we have, for example, the star formation history of the universe, and on the right panel we have the delay time distribution. So this is this is age of the universe. So this is today, and this is early times. So this is the and on the right panel is the delay time distribution. That is the distribution of times between formation and mergers of these binary systems. So there are essentially two things that are important if we are measuring systems at any point in time, say today, at 13 gigayears since the beginning of the universe. We are getting merged things that have formed at different points in the history of the universe, right? So things that have formed here essentially and are merging today essentially have long delay times, whereas things that are formed at this time and we see their mergers today have short delay times. And even though and so the important thing to note is, of course, that even though the delay time distribution is such that there is higher probability at low merger times and low probability at long merger times, the star formation history of the universe, there was much more star formation at a longer time than there is today in the universe, right? So it's basically an interplay between the distribution of merger times today, when we measure it, is essentially a convolution of the star formation history of the universe with this delay time model. So if we pick any delay time and alpha, we will essentially measure and we say for starters, if we are looking at all the mergers that are happening at redshift 0 or right now, the actual delay time distributions of the objects that we see merging will look something like this, right? And for different models, the shape of actually the merger times is going to be essentially different. Now, these are, of course, the merger times. The binary mergers don't, of course, come with a tag of what their merger time was. So how do we actually tell what their merger times possibly are? What we essentially note is that the merger time distribution that is measured at any redshift essentially picks out different types of galaxies, right? So because the cosmic star formation is, of course, happening in these galaxies, right? And we are just adding all the star formation in different galaxies and making that full cosmic star formation history curve. Different parts of this curve essentially map out to different. Yeah. So long delay times so things that have had long delay times will preferentially be in red galaxies. And if neutron star mergers or black hole mergers have short delay times, they will preferentially be in star forming galaxies. Simply because, a red, massive red elliptical galaxy has formed majority of its stars around redshift 2. So if you are seeing most of your mergers in red and dead galaxies, essentially you're saying that the underlying delay time distributions are very long. Whereas if you see them in, so this is a typical star formation history of a red galaxy, of a red elliptical galaxy. Today it's red, its star formation peak was much earlier. So if you see mergers there, you're more likely to be long delay time versions. Whereas if you see them in spiral galaxy, their star formation rate has still not started forming. They're still has falling. They're still forming stars very rapidly. So essentially, short delay time ones are more likely to be in sort of high star forming objects. So the merger rate of a given galaxy is just for a given galaxy is just a convolution of its star formation history with the delay time distribution. And of course, the overall merger rate and where they lie will also depend on the distribution, the distribution of galaxy properties themselves. So essentially the luminosity or the stellar mass function of galaxies, right? So how many galaxies of a certain kind do we actually, of a certain stellar mass or star formation rate do we actually have at given redshift? So the luminosity function of galaxies is of course intrinsically related to the halo mass. So the distribution of galaxy masses is related to the distribution of halo masses, which comes from the underlying cosmology in the universe. So essentially, where we see the galaxy mergers, and what is the stellar mass distribution of the sites of binary mergers is determined by essentially a convolution of the rate of the galaxy merger rate and the halo mass function. So given this basic structure, we can then try to model the binary evolution in we can try to model. Sorry, there was a question. Should I answer it now or later? So I'm seeing a question by Ramiz in the chat.
Yeah, please answer.
Yeah, so could you explain why there's an abrupt fall in the delay time distribution below 1 giga a year or so?
I'm sorry. It was only because someone said online participants can type your question. You can answer it whenever you want. But I don't want to interrupt your talk. Sorry.
Okay, no. Yeah, I can quickly answer the question. It's fine. So are you talking about this one?
Yes.
Yeah, so it's not an abrupt, it's a particular model. So the model is parameterized by a minimum delay time and a power law fall off. So this is just the minimum delay time. So if you change that, there's no reason for it to be at 1 gig a year particularly, but there is some,
Yeah, but it feels a little unphysical, no? In the sense, the maximum is immediately above that, according to this curve. So it would.
So this just comes from, right. So this power law fall off essentially just comes from what the orbital separations are of galaxy, of binaries when they form. So that part just comes from, so there's no, right. So I think the minimum delay time is as such not comparable to it. It's just that right. So is there a reason why?
We can discuss this later
offline
if you like. Yeah, let's not take away from your talk.
Okay, no problem. Okay, so right. So modeling the binary evolution, right. So based on this, we can essentially model the binary evolution, in a cosmological volume. So we can try to make mock simulations of where these different binary mergers lie, using a cosmological simulation and basically populating the entire cosmic web, given we have some way to put galaxies into the cosmic web. Of course, you can do this in a full hydrodynamical simulation. So one of the things, but there are challenges to that where we don't completely, of course, understand the full galaxy formation. The galaxy formation models start to play a very important role, our understanding of galaxy formation. But in a more statistical sense, we can also use dark matter only simulations and semi-analytically model galaxy formation on them, which has also been done quite extensively. And then we can also embed binaries onto these. So we can take the next step and also start to embed binaries in these galaxies. So we use the universe machine simulations. So these to do just exactly that. So we took these large box simulations, which starting with sort of 250 megaparsec boxes, cosmological volumes that are evolved from redshift 49 to 0. And these simulations essentially populate a dark matter only simulation with galaxies. So it's based on a semi-empirical model. The population of the connection between the galaxies and the halos that formed in this box is based on a semi-empirical model that basically parameterizes, the correlation between the star formation rate of a galaxy and the mass accretion rate of the parent dark matter halo. So just in case you don't look at these simulations very often, each of the nodes in this web is a dark matter halo, and within each of those nodes, a galaxy will form and evolve. And basically the galaxies, and basically we populate this dark matter simulation with galaxies by relating the mass accretion rate, the dark matter mass accretion rate of each of these halos to the star formation rate of the galaxy. So this was a large work done by Behrouzi et al. A few years earlier. It's a 43 parameter model, and it has been constrain using, almost like a lot of observations of, basically the bias of galaxies, the cosmic star formation history, the measured stellar mass halo mass relationship, and a series of such observations about galaxy properties and the underlying cosmic web. So we use these simulations. So given that these are embedded on dark matter simulations, we basically have the entire merger history of a particular galaxy through time. Right, so we have the merger history of the halo, and therefore we also have the merger history of the stellar mass growth history, the star formation growth history of each of the branches of that galaxy.
Yes.
So universe machine essentially provides us with stellar mass halo mass connection, and also just the full star formation history of every single galaxy. And what we then do is essentially take the star formation history of these galaxies. So take each individual galaxies in the simulation and populate the star formation history of that galaxy with these binary evolution models, right? So so essentially what we have is a simulation where every galaxy is assigned a merger rate based on the parameters of the delay time model that we use, right? So we can then essentially vary the parameters of the delay time model and look at the properties of host galaxies today, right? So for example, for short delay times where the minimum delay time is of the order of 10 million years here, 100-ish million years here, we see that most of the galaxies in the stellar mass specific star formation rate will lie on the star forming arm of the galaxy of this in this plane. So this is low star formation rate, and this is high star formation. This is high star formation rate, and this is low star formation rate. So these are all going to be in high star forming galaxies, and the 1 point over here is NGC 4993. So for longer delay time, we see that these galaxies, of course, tend to move towards higher stellar mass. So we can basically build up in this way, we can basically tune our delay time distributions and try to use observed distribution of host galaxy properties, so to try and constrain what the underlying delay time distribution should look like. We can also start to probe properties of its host dark matter halos, like given a delay time distribution, we can start to see where what is the distribution of their dark matter halos, and also just which is, this is the mass. This is a proxy for the mass of the host dark matter halo. It's the halo's velocity dispersion. So things which have long delay times, of course, tend to lie in higher mass halos, just simply because the centrals of high mass halos have build most of their star formation, most of their stellar mass in early time, have massive elliptical red galaxies at their center. Similarly, they are also more biased objects. Therefore, this parameter delta, which is essentially a measure of their local density, their local density measurement, they also tend to be in locally more dense environments if the delay times are longer, whereas if the delay times are shorter, they tend to be in less dense environments. And all of these relationships between density and the delay time distributions are essentially just coming in from the relationship between density, halo mass, and galaxy properties in a sense. So we can use these to simply, constrain how many events will we need to sort of get constraints on the minimum delay time and the slope of the distribution. And then we can also ask simple questions like, how do we, using these simulations, we can also ask simple questions like how do we, if we had a sense of host galaxies, how well can we tell differences? How many events do we essentially need to tell, say, whether these objects follow this galaxy stellar mass or the galaxy halo mass or star formation rate, or are just a random sampling of galaxies in the universe. And we found particularly to distinguish whether the binary mergers follow galaxy stellar mass or star formation rate, we only need of an order of few tens of host galaxies to start making these inferences. So this is just the distributions here shown for essentially galaxies that have been picked with different mergers that have been picked that follow different weightages of galaxies. So just reiterating, just the overall distribution in the universe of things that live in that if mergers have short delay times versus they have long delay times, the overall distribution in the universe will look significantly different, right? So these long delay times will be much more clustered and more likely to be in high stellar mass, massive halos and denser environments, whereas shorter delay times will closely follow star formation rate and will be much more diffuse in the universe. So in the view of time, I'll just move on to the last part where we've been looking at, so the earlier part was sort of based on NGC 4993, but was mostly a theoretical modeling to incorporate these in simulations and use them as mock catalogs of binary mergers. But recently we've also been using actual data from short GRBs. So short GRBs, NGC 4993 was the first actual event which directly linked a neutron-star merger to a short GRB. But we expect that short GRBs, essentially, it's been thought for a while that short GRBs are also likely products of binary neutron-star mergers. And we have a lot more short GRBs than, currently we have electromagnetic counterparts for neutron-star mergers. So we can start by looking into the host galaxies of these short GRBs and start to see what kind of constraints do we get from these objects. So we looked at a host of we looked at the host galaxies of about 68 short GRBs. So these are 68 short GRBs that have confidently associated host galaxies with them. So this is a new catalog that was published by Wenfei Fong, Anya Nugent et al. And essentially following up GRBs using Swift over the last decade or so, and basically getting confident association of host galaxies with these short GRBs. And for each of these galaxies, we can actually, directly fit some of these galaxies. I should say they have both photometric band imaging, and also they have some of a small fraction of them also have spectroscopy. So we can we do SED fits and essentially get a star formation history for these galaxies, and using the star formation history galaxies and then populating them with these delay time distributions, we can actually start to constrain what we get for the minimum delay time and the slope of the distribution using these objects in the universe. So these are actually the first constraints on the delay time distribution of binary mergers using host galaxies of short GRBs. We find a minimum delay time of about 200 million years and a pretty steep slope of around minus 1.83. Of course, the error bars are pretty large. The slope, I did not mention, the slope is expected to be either in the range of -1 and -1.5, we tend to find a slightly steeper slope, but it's still consistent with -1.5 essentially. So given these parameters, constraint parameters, we can then actually also predict a cosmic merger rate of binary neutron stars. And this is essentially the merger rate that we predict using the delay time parameters that we get. So essentially, it'll be interesting going forward to see if from these observed, constraints from the observational data of short GRBs, if we can, if they are consistent with what we get from GW, and also from gravitational wave science and so on and so forth. So the other thing that we want to do currently is essentially we have these host galaxies for these 68 events. So these are all the measurements of the stellar mass versus redshift, the specific star formation rate versus redshift, and the metallicity versus redshift of these host galaxies. And we can see how they essentially compare to our expectation from galaxy formation models, essentially, right? So, given if we assume that they form star formation rate, and if we populate galaxy star formation histories with these delay time distributions, do they essentially agree with what we were expecting from what we expect, how we expect stellar mass and star formation to build up from galaxies? So one thing that we were currently finding is that when we populate the simulations with these delay time parameters, while the star formation rate distribution of these galaxies agree very well with what we predict from simulations, from these models in a sense, particularly for low delay time, low merger time, low minimum delay time. So the darker colors are shorter delay times here. And the blue band is basically the data. And on the left panel is a specific star formation rate, and the right panel is the stellar mass. But we see, so the star formation rate distributions do agree, but it seems like the stellar mass distribution, these short GRBs, tend to live more in lower mass galaxies than what we expect from populating these simulations. So if you looked at this curve, a lot of these galaxies where the short GRBs are being seen are of our sort of LMC, like the large, our half stellar masses around the Large Magellanic Clouds. And this is actually opposite to sort of like the bias that we would expect, that you would miss out faint galaxy hosts. Here we are actually seeing that they're, so it cannot just be an observational bias, because we're essentially we have an excess at the lower mass range. So here we do some comparison. So we do some comparison with different delay time distributions in the universe machine simulations. And in the bottom, we've also made some comparisons with illustrious TNG, which is a hydrodynamical galaxy formation cosmological simulation. And while the star formation, stellar mass distributions might still be better, more consistent with what we observe in data, the star formation rate distributions are quite different. I'll summarize. Yes. So I'll summarize and I'll take questions. So basically, the interplay of galaxy evolution and binaries is certainly in this day and age something that is the future of which is very exciting, and sort of understanding these connections will help us better predict, the hosts of mergers, understanding their localizations, which I did not go into much of the details of. We'll understand their biases using these kind of approaches. And essentially, we can understand different formation channels, and also it'll tell us about what, it will also help us reinforce or, recheck our understanding of what is the connection between galaxy evolution and whether we understand galaxy formation itself well enough, and if it's consistent with what we are learning from these binary merger distributions. Of course, the future is to essentially take these forming these mock galaxy mock binary simulations further to do all kinds of things, including cosmology, including hosts that followed different formation channels, and how, for example, they would trace globular clusters or stellar clusters, or if they would, or how supermassive black hole, or if we could even embed supermassive black hole mergers into these simulations to sort of understand these objects and so on. So with this, I'll end, and I'll take any questions that you have. Thank you.
Thank you very much. We have time for many questions. Maybe I will invite questions first from students and younger colleagues.
So I wanted to understand the motivation of that probability distribution of merger. So I think that's coming from theory. So how that particular distribution is motivated? Why do we assume such a distribution?
Right. So I think, right. So basically, if you look at the distribution of, right. So it essentially, the power law distribution that you get is coming from the distribution of orbital separations in which binary systems form. So then given just the separation, which has been actually modeled from simulations, if you look at the separations, and then if you just convert it using sort of a Kepler's law evaluation to a distribution of times, you get the power law distribution in time, right? Now, the minimum delay time is essentially, I think, and if there's some people who work on star formation simulations, they'll probably be able to add to this and correct me if I'm wrong. So the minimum delay time also comes from the fact that it is actually not completely clear if black holes will, or for example, black holes or neutron stars will merge at all in the so that is why there is a minimum delay time that is essentially set, sort of forms like a barrier between that, say you can extend that to whatever value that you want if you at all see a presence of not having mergers that are shorter than some delay time in the first place, right? So that's essentially where it comes from. Yeah.
Thanks.
Yeah. And yeah, anyone who's closer to star formation simulations or who thinks about this more, please feel free to add to that.
Yeah, that was a really great talk. That was such a nice overview. I just have a question about the delay time distribution. Like, we have some constraints on it for neutron star binaries, at least from measurements of, double neutron star systems in our own galaxy. So like for 20 of them, we know the merger timescales and their sort of approximate ages. Is that, have you looked at, or has anyone looked at whether these delay time distributions are kind of consistent with like what we see for double neutron stars in our own galaxy?
Yes. So for the short GRB measurements that we did, so we did check to see if they're consistent with the delay time distributions that we are getting from our own galaxy, and they are consistent within the error bars, although the ones within the galaxy tend to show hints for much. Actually, the minimum delay time is probably of the order of a few, is sort of closer to around 50-ish or 10 to 50-ish million year, whereas we are getting something a little longer. So they're slightly inconsistent, and I don't think we completely understand why that is. But the slopes are essentially
questions by DCJ asks, how does merger in hierarchical structure formation factor into delay time distributions?
Hi, Pratik, I couldn't hear the first part of your question.
So it's there on chat also. So BCJ asks, how does star
Yeah, I
formation
can-
triggered by galaxy?
I think I can ask because I think your voice is breaking. So maybe I can ask. So, hi Sushmita, it is Bhalchandra Joshi here. So I was just wondering that how does the star formation, which is not in an isolated galaxy, but star formation triggered during a galaxy-galaxy merger, affect the delay time distribution estimation in your method?
Right. So, yeah. So in the simulations where we have the full merger history of a galaxy, so how this will be tracked is essentially if two galaxies merge, right? So for a short span of time, the mass accretion history of the halo will also spike, right? So that will lead to a spike in the star formation rate of the galaxy. So that will essentially be captured in the star formation history of the galaxy as, you know, a local increase. And we are basically, in a sense, populating the number of binary systems proportional to the star formation rate for a galaxy at a given time. So it'll be, so that should be taken into account. Of course, you know, the galaxy formation model itself is, there might be some small things that we correct for, but it is going to be taken into account as a sort of a peak in the star formation history, localized peak in the star formation history during a merger. Yeah.
Okay, thanks.
Yeah.
I was talking about the,
Oh, yeah. So sorry. Yeah. The y-axis is just the, you know, this is just the distribution. So it's just like, this is the cumulative distribution of galaxy star formation rate. So it's just, of course, it's a fraction in a sense. Yeah.
Yeah. The other question I had was, typically I've seen star formation rates in the, you know, in units of something like billion solar masses per giga year or something like that. What is the unit here? Because if you're taking logs, I'm assuming you've taken some kind of.
Yeah. So there's the unit here is basically solar masses. This is actually number per year because it's specific star formation rate. So it's divided out by the galaxy's stellar mass as well.
Okay, thank you.
Yeah.
If there are no other questions, I have a bunch of questions. So this is about this very interesting estimate of the delay time to be around 200 million years based on short hard gamma ray bursts. This is very impressive, but if you are going to make such estimate, isn't it there's a problem, right? We know that 817 was the fluence was like 1,000 times smaller than the short hard gamma ray burst that we typically see. Therefore,
okay.
So did you guys actually put in that? This is a very unique event compared to what we generally see as a
I don't think we took info. So NGC 4993 is a part of like GW 1780. 817 is a part of the analysis, but we actually did not include information about the fluence of the short gamma ray burst itself. In that sense, we did not factor in the. Yeah, we didn't. In that sense, we have not factored in that the fact that short GRB, that particular short GRB was very different. I was not aware of that somehow, that it's very different in that sense.
Okay,
as well.
no, not a problem. So it's just a follow-up of Maria. This is about, I thought you had a slide about the predicted, BNS merger rate based on that. And Maria was kind of asking how it kind of is consistent with what we know from the double neutron star binaries that's expected to merge, as you correctly pointed out, something like 50 million years or so, right?
Yeah.
So that has definitely something to do with the metallicity, sort of related to now star formation and all that. So you should be able to kind of get away with, even there are not within the error bars, you should be able to get away from that, right?
In the sense that because, so you're saying that the ones that we are seeing in our galaxy are in a sort of high metallicity environment.
Right.
So there we would expect a different, I mean, yes, off the top of my head, I don't see why that would make the delay time shorter. But yeah, I mean, I would have to think about how that is actually connected to the.
We can take this offline.
It might be that I'm not sure exactly what the connection, but it might be related to that as well. Yeah. So it would be useful to see sort of how the delay time changes as a function of different galaxy properties. That
Yes,
would be really
because you kind of mentioned that if you identify 10 host galaxies, that can essentially tell you, about kind of the straight, I mean, the way you are bringing in, right? The halo mass kind of accumulation, right? That's what goes into the star formation rate and all that, right? So, I just following up one. So if some of these events are occurring in, say, the active galactic nuclei has been proposed, right? This will get into trouble for you, right? Because you assume these events are either in the field of the galaxy or maybe in globular, clusters. So you can't distinguish those things. But that for the AGN will be very different. So that can
so that is actually a very sort of like an extension. So in the sense that here we are really just saying that let's say that they follow star formation in the galaxy, right? So they just follow the stars, but you can, right? So you can use sort of, you can use a completely different model, particularly based on simulations or some analytical HODs or something that you have, to say that what is the properties, the current properties of galaxies that live in AGNs, for example. And you could then try to see if the distribution of galaxies are the different distribution of host galaxies of AGNs, and you can try to see how consistent they are. So so that's sort of like, here we assume star formation, history, evolution, but you can make those comparisons also in a similar way, sort of understanding how AGNs live, what kind of galaxies AGNs populate.
I was kind of trying to argue that if you are going to say electromagnetic counterparts from, black hole mergers, the easiest way will be to go to AGN activity, in the disk or something like that, because it will be fairly difficult to get it in the field with an electromagnetic counterpart, unless you are, there is some sort of a circumbinary disk and all that, which is difficult to sustain. Therefore, if in O4 or O5, you start seeing black hole binaries with possible EM candidates, people will tend to argue that these are from, AGN disk rather than, out there in the field or in clusters. There's no way you get electromagnetic, processes happening to a black hole binary if you're just out there in the field. Again, we can
Yes. I mean, this was not, this particular thing was not for black hole binaries. It was more for neutron stars. But for black hole binaries, why? I don't think why it would specifically lie in AGNs is that expected.
So if that's in the disk, it can interact with those material, and that can, I mean, there's, for example, 190521, there's a possible suggestion that it may be associated with an AGN. They have a CTF candidate.
Yes.
It's going to happen, most likely not. But down the line, when the numbers start increasing, that direction people may want to take, right? I mean, that's.
I mean, yes, it's interesting. It's not clear if the, I mean, I guess I guess there's a lot to understand about the formation.
The sheer number of black holes going to overweigh BNS events. So anyway, it doesn't matter. Okay, thank you very much. It was a fantastic talk. Let's give 3 cheers to her again, and thanks again.